Okay, so good morning everybody and very welcome to this compiler's talk early in the morning. My name is Ionut Balosin, I'm software architect, I work for Luxoft and I also conduct technical trainings, especially on the performance and tuning field and on the software architecture. If you want to get more details, you can visit my website, ionutbalosin.com, or my Twitter. What's the agenda for today? I took a lot of topics. Actually, we will go through each of those. We will first start with the Java code. We will zoom inside the optimizations that happens under the hood from two compilers' perspective. For example, clang LLVM and just-in-time C2. At the end, we will close with few conclusions. What was my motivation to drive this experiment? Because it's not quite easy. I'm a big fan of Richard Feynman, and he wrote a book, The Pleasure of Finding Things Out. This was my main motivation. What happens under the hood? How those two compilers optimize similar code under the hood, and also on top of that, or besides that, I think that learning based on evidence driven by experiments, it's the best way to learn things. What are the key points out of this talk? First, it's about optimizations. We will zoom inside few optimizations that are generated by those two compilers on the Java side and on the C++ side. On Java side, we have just-in-time C2 in HotSpot, and on C++ side, we have LLVM clang, a very, very interesting compiler. So we will see from two different perspectives those optimizations. And also, we will challenge how powerful are a bunch of optimizations against the others. However, by powerful, I don't refer to the timings. Why? Because timings might not be very important. By powerful here, I mean to the patterns. What are the patterns behind those optimizations? And this is a reminder. I don't intend to make this presentation a battle between C++ and Java, because you might think in that way. It's not my intention. My intention is just to reveal how these compilers optimize the code under the hood. And why this might be a matter of interest? First, because of performance. We talk about performance, so we need to understand what happens under the hood, which one is better, and what's the context around. And the question might be why I took LLVM clang. Because LLVM clang, it's a wonderful compiler. Probably it's one of the best AOT compilers. It compiles ahead and generates the binaries. And also, just-in-time C2, even if not is a state-of-the-art compiler, because you might have heard about LLVM and Graal compiler. I agree, that one is a state-of-the-art compiler. However, the most of our code in productions, it's still based on JIT C2. We are still using HotSpot in production, so that's why it's still a matter of interest. And also, on top of that, Java is moving towards AOT. There is JEP 295, and they added support to compile ahead. In terms of compilation process, it's very different between Java and C++, more precisely between just-in-time compiler and clang compiler. Why? Because on the Java side, we have the source code, we have the bytecode, and during the runtime, there is the interpreter that initially kicks in, and the code is profiled, and the just-in-time compiler optimizes even more the code, C1, C2, and generates at the end the native code. And all happens at runtime because it's about just-in-time compilation process. As opposite, the clang does everything ahead. With clang, you have a C++ source code, and it kicks in clang. It starts with the front end. It goes into a bunch of optimizations based on IR, intermediate representation, and then generates the code, and everything happens ahead. There is no execution for the application. It's exactly like you compile a C or C++ source code. Before to zoom inside the topics, let's share with you some of the methodology and the pitfalls that I learned driving this experiment. First of all, it's not a comparison between apples to apples. Why is that? Because we were written Java code and we were written as well C++ code. However, we try to be as similar as possible, but it's not perfect, and we can't do that because each programming language has its own specifics, and those specifics influence as well the compilers under the hood. However, the benchmarks that we used on the Java, we used GMH, Java Micro Benchmark Harness. C++ was based on Google benchmark. Those two benchmarks have very different heuristics because it's about AOT versus just-in-time compilation process. Also, it's not fair to conclude out of this presentation that one, for example, C++ or Java is better than the other, because I used only two compilers, one from each side. I use Clang, I use C2. There are also a lot of other compilers on C++, GCC, MSVC, on Java there is Glar, Farcon, the J9, so it's not fair to conclude one is better than the other because it's not representative. However, I run all the tests on the single machine, my laptop, so also the timings might be different if you run on different architecture. And also, as you will see, in few cases, it's about a comparison between 2-something nanoseconds versus other 2-something nanoseconds, slightly different. In this case, I would say that fast enough, it's fast enough. When we zoom inside the decimal nanoseconds precision, probably it's end of story. We can't say one is better than the other. All of this being said, let's start with the first case, sequential sum of n elements. Here is the Java source code. In the Java source code, we have a very simple method that basically iterates through an array and computes the sum of the elements from that array, and it returns the sum. If we compile and run this and we zoom inside the JIT C2 code, this is assembly, but it's not a very big deal because I structured in a very simplistic way, and I'll try to explain each piece out of it. So the JIT C2 starts with a scalar preloop. What is the scalar preloop? Every time you write loops, it peels few iterations out of the loops. Basically, it extracts first iterations just before the loop. And this is, in this case, it adds, for example, the first add. It just the first add addition. And this is useful from the memory alignment and CPU caching perspective. And then our main loop, as you can see, it's unrolled. What means unrolling? Basically, instead of iterating one by one every loop cycle, it iterates, as it is in this case, 16 additions per loop cycle. Why is this optimization important? Unrolling the loop. It's basically, it minimizes the number of jump instructions because we have less loop cycles. On top of that, if the instructions within that loop cycle could be triggered in parallel, there is a good opportunity for the CPU to execute them in parallel. And if there is a remaining, because probably the array length it's not a multiple of 16, for example, the remaining is handled one by one until it reaches the end. So this is how the initial loop it's desugared during the runtime and it's optimized. Now let's switch to the LLVM clang. What does LLVM clang? The LLVM clang starts with the main loop, which is based on the same unrolling principle. However, a big difference this time, as you can see, XMM registers. These XMM registers are registers that could store 4 integers. So LLVM clang uses vectorized operations. It still does loop unrolling, and it tackles within one loop cycle 32 integers, as in comparison to the JIT C2 that tackles 16. And if there is a remaining which is less than 32 but bigger than 8, it's still a post loop. It still ends with a post loop which is vectorized again, so it adds 8 integer per loop cycle. And if the remaining is less than 8, it tackles one by one until it reaches the n array length. If we have to get back and summarize the patterns, in case of JIT C2, it starts with a pre-loop, it tackles one by one. In the Scalar main loop, it does 16 per cycle, and the remaining, it's one by one until it reaches the length. However, as you might see the note, this is not a general purpose pattern for optimizing the loops because it doesn't use vectorization in specific this case. Let's switch and see the LLVM clang. LLVM clang has the vectorized main loop, which tackles 32 integers per cycle in this case. It continues with the post loop, which tackles the next integers 8 by 8 per loop cycle, and if there is a remaining one by one until it reaches the end. In terms of figures, the benchmark comparisons, I took for different array sizes, like 10 multiplied by 10 of power of 3, 100, 1000, and in all cases, LLVM clang was better. Why was better? In essence, because it relied on vectorized, on SIMD operations. As you can see, XMM registers. This is, and of course, the timings are dependent on n size. So bigger the n size is, it impacts the timings and the throughput. In conclusion, as we already saw, LLVM clang uses vectorized operations. It is based on XMM registers for the main and the post loop. The last loop, it's one by one until it reaches the end because there is no other way. On the other side, JIT C2, on the Java side, even if it does loop peeling, I mean it unrolls the loop and peels few iterations before the main loop, still couldn't beat LLVM clang because it doesn't use vectorization. And the question is why it doesn't use vectorization, because it should, right? And it should be legitimate to do that. And the answer is this. It was a specific case where the JDK guys decided to disable the vectorization because the generated code wasn't so beneficial from performance standpoint. And this is the task. The task on their Jira system to consider re-enabling it back. However, until that moment, it still uses Scalar operation. It's not based on vectorization. And because we are Java guys, and it's a Java conference, I don't want to give you the impression that JIT C2 doesn't do any vectorization at all. Let's visit few other cases where Java still, JIT C2 in essence, does vectorization. The first case is when you sum, for example, two arrays, like you have array A and array B, and you count the sum in C. There is a setup method which initializes both arrays, very simple, and at the end, at the bottom, there is a benchmark method which says C equals A plus B. So it traverses both arrays and returns the sum. What we have in the C2 version of the assembly generated, as you can see, this case, it's vectorized and it uses YMM registers, so even bigger registers. So in one YMM register, it spreads across 256 bits and it could store, for example, 8 integers. As you can see, the main loop is unrolled, and it is based on this YMM register, and it tackles 128 numbers per loop cycle. So it's incredible, powerful. This is one case. It still have the post loop and the last loop, the remaining one. But here I decided to include in the slide only the main loop, just to give you an idea that it still does vectorization in a very wonderful way. The next case is when you have a constant and you add that constant to all the elements array. For example, you declare an array and you iterate through it, first to initialize and at the end to add to each element array entry that constant. And this is the benchmark method in essence. So the benchmark method, the last one at the bottom of the slide, it does that and returns the array. What is the code generated? It's very similar to the previous one. It unrolls the loop, and within one loop cycle this time, it tackles the same 128 elements array. So 128, again, until there are some remainings, and those remainings are handled as it's here described. So it starts with still a pre-loop where it peels few iterations out of the main loop. As I was saying before, it's because of the memory alignment, the CPU caches, and the vectorized main loop. It's in this case was 16 multiplied by 8. It's 128 additions per cycle. And it continues with a vectorized post loop if there is a remaining which is greater than 8 but less than 128. And still, if there are a few of them, it's the last loop, Scalar post loop. Having all of this shared, you might have wondered, but why those numbers? Why this 16? Why this 188 and so on, right? Because there are some magic numbers. When the compiler decides to do this kind of optimization, it should take into consideration few heuristics. For example, the code size generated, and all of the others. So that's why, and the CPU, of course. And that's why it decides the unrolling step, if it is 16, if it is 128. So it takes into consideration the code size generated and the target CPU the program runs on. In terms of benchmark comparisons, the figures for summing two arrays and a constant added to all the elements array, we can see that for the same size, we have similar timings. For example, 61.9 versus 62.4, 30.0 versus 31.6. I would say that's fast enough, it's fast enough. We can't say one is better than the other, because probably if we repeat again the measurements, we will get slightly different timings, but very close in essence. Which leads to the conclusion that when both compiler relies on the same technique or patterns like unrolling, like vectorized operation, the performance it's closer. The next case, it's the case about sequential sum of n integers. What that means? Let's suppose we have a method, and in that method, within the method, we return the sum of all elements from 1 to n. So it's basically 1 plus 2 plus 3 plus 4 until it reaches n. And it returns the n. What or how just-in-time compiler C2 optimizes this during the runtime? It still starts with the Scalar preloop. It does only few additions before the main loop, and then the main loop it's unrolled with a step of 16. So basically it adds the first 16 and the next 16 and the next 16 and so on within the same loop cycle, and the remaining, because probably there is a remaining, it's tackled one by one until it reaches the end. So this is how C2 optimizes and runs during the runtime the initial source code. On C++, LLVM clang, what it does, it realizes oh, oops, there is a formula, right? Because we know from school that if you add 1 plus 2 plus 3, it should be a formula, a reduction formula. So LLVM clang realizes there is a formula, right? And it still doesn't do any loop. It completely removes the loops. As you can see, it's still a reduction formula as we know from schools. So it reduces everything to the formula over there, n multiplied by n minus 1 over 2 plus n. It's the formula that we learn from schools. In terms of figures, LLVM clang, of course, it's best. It's best in all cases because it's just a formula. There is no overhead or depending. It doesn't depend on n size. And the performance or the response time, it's actually constant. It's 2 multiplied by 10 of power of minus 6. In comparison with C2, C2 depends on n. Bigger the n is, more impacts the performance. And the conclusions that we already talked about, LLVM clang uses that reduction formula optimization. It's not dependent on n. In case of C2, even if it does peeling, I mean, it unrolls, it peels the first iteration from the loop. It starts with those and then continues with the main loop, which is unrolled, still couldn't beat the clang because the clang uses that wonderful optimization. And when I looked into that code, I was a bit puzzled and I posted a question to OpenJDK forum and some asking why C2 it's not possible to do that optimization. And somebody replied saying that hypothetically JIT C2 could do that, right? Because it's basically an optimization at the end. However, it would need more advanced loop analysis, and this kind of optimization it's not present in JIT C2, and to my knowledge it's still not in their roadmap, so probably it won't be added because there is a big focus towards Graal compiler, so probably JIT C2 won't benefit of new optimizations or completely new optimizations despite of vectorization enhanced support and other intrinsics. On the other side, LLVM clang does this optimization, which is based on scalar evolution and loop optimization, which happens, and as you saw, it's very efficient in this particular case. The next one is fields layout. What we have in case of fields layout, we have 3 cases actually. Let's start with the first one. In the first one, what I created, it's a comparison between a Java class and a C++ struct. In both cases, we have the vanilla class from the Java contains 2 shorts, x and y. And top right, you have the layout in the main memory, how it looks like. So basically, it's because we are in Java, every object has a header, and this particular case has 12 bytes because I was using 64-bit architecture and compress subs enabled. So basically, the class and the mark together inside the header are spread across 12 bytes. And then follows x and y. So in total, a Java instance measures 16 bytes. In comparison, the C++ struct has only 4 bytes. However, I didn't include in this because there is still a header for the struct in C++ when you allocate. A header which says how many bytes they are allocated, but for the simplicity of this presentation, I removed that word header. And let's suppose there are 4 bytes. If we get back to the hardware and understand a bit how the hardware, the caching on the hardware it's split, it's a hierarchical like L1, L2, L3. And for example, in L1 case, it's split in cache lines, and every cache line has 64 bytes. So basically, the L1 cache, it's split in those 64 lines, 64 bytes line length, and there are 512 such lines. So basically, if we get back to our instance footprint, in case of Java, it measures 16 bytes. There are 4 such instances that are spread within the same cache line. In comparison, C++ struct because it has 4 bytes, there are 16 of them that fits within the same cache line. And having this understood, this is the test scenario that I drive. So basically I created an array and I try to traverse that array by accessing x and y and returning the sum. Very, very simple example. And in terms of performance, because I forced all the instances to be in the CPU caches, and in case of LLVM clang, I got a better actually performance because there are microseconds per operation, so it took lower, implicitly better. Why? Because probably it was impacted by the number of cache misses. More instances fit inside one CPU cache line, it's better. It's about object locality. On top of that, on Java, we can't have like array of structs. We have array of objects. There are additional pointers, additional indirections versus the C++ case. The next one, because I was saying initially that we have 3, it's comparing a padding. What has padding? I decided this time to add an explicit padding, those sequence of longs, L0, L1, L2 until L7, so basically 8 longs. Why particular 8 longs? Because they in total have 64 bytes, so basically they could spread across the entire CPU cache line. However, be careful because the order you declare fields in a class, it's not the order they are at the runtime. And as you can see, the top right, Y, it's right after X. It's not in the order that the programmer declared after the bunch of longs. So Java does fields reordering, and we will talk a bit later why it does field reordering. Basically just to minimize the object footprint and to prevent misalignments. But we'll get back to this topic. In comparison, C++ doesn't do any fields reordering. However, it adds a padding before L0, as you can see in the image below. It starts with X, Y, and it adds a padding between L0 because otherwise L0 would have been unaligned. So L0 should start with an address multiple of, for example, in this case, 8. And getting back to the CPU principles, having the same structure, the same cache length size, we can see that in this case, an instance of the Java measures 80, like here, it measures 80 bytes, and the C++ instance measures 72 bytes. In conclusion, in both cases, there is only one instance that could be spread on the same cache line for the C++ and the Java side, but with a very important similarity. Both X and Y fields on the same cache line. So requesting X, you have Y implicitly on the cache line, so you minimize the number of misses. The benchmark is very similar. I created an array, I traversed the array, I accessed X and Y, and I returned the sum. And the figures are, for example, 174 versus 173. So basically fast enough, it's fast enough is the other case. In both cases, the timings are similar, because probably the number of misses under the hood are comparable, so all the things around. So not a big discrepancy. The last case is because we saw Java does fields reordering, and I don't want to do that. I don't want to happen the fields reordering. And how you can do that? One tactic is just to do subclassing, because Java doesn't reorder fields from the subclass with the fields from the base class, actually. And in the base class on the Java side, I declared X, a bunch of longs just to cover the entire CPU cache line, and then in the subclass, in the hierarchy which extends base, I declared X. And as you can see, X it's not next to Y, it's not to X, sorry. It is after the bunch of longs, and here it's a padding after X and between first L0, because all the types, all the fields in Java should be typed a line. For example, L0, it's a long, should be typed a line. And the object itself, at the end, there is still a padding after y. It's a padding from 82 to 88 bytes, because the object itself should be aligned to 8 bytes in this case, because otherwise we will have misalignments. So in total, an instance of that hierarchy on the Java measures 88 bytes. In contrast, C++ still adds a padding before L0 and the padding after Y, because it's the same story, that the field should be aligned and the instance itself should be aligned. The only difference, I would say, is just the header. In Java, we pay the cost of the header of the instance. In total, C++ struct measure 80 in comparison with the Java instance, which has 88. If we get back to the CPU, one CPU cache line stores one instance on both sides. However, there is a difference from even the previous case, because now X and Y are not on the same cache line. It's X, the padding, a bunch of longs, and then Y, it's on the other CPU cache line, because both are not closer enough to fit within 64 bytes. The test case is similar. I traverse the array and I do the sum x plus y, and the timings are almost comparable, 1.96 versus 1.94, so fast enough, it's fast enough. So these are the conclusions out of it, and this is not particular to the compilers, by the way, it's particular to the language itself. Java does fields reordering, however, we pay the cost of those indirections and we pay the cost of the header. LLVM clang doesn't do fields reordering automatically, however, because I was using a struct, I was using an array of structs, so it was implicitly there were few indirections. And now, because we saw the fields reordering, and the fields reordering, of course, impacts the performance, so you should be aware when it's good and when it's bad. What are the cases where fields reordering might help programmers? So let's stick to the Java in this case. So the fields reordering, it's good because it improves the overall size of the object, because it reorders the field like you saw, short, and longs. It implicitly minimizes the footprint, so it reduces the paddings in between fields. And also it prevents unaligned access to those fields, because in Java every field is typed aligned, and the object itself should be 8 bytes aligned or 16 bytes aligned. So that's why we had that padding at the end. And also regrouping the fields so they fall on the same cache line as we saw in the second example. Even if we declare y, the short y at the end, it was reordered and it was laid out after the x. So both x and y falls on the same cache line. If there are only readers for x and y from multiple threads, we benefit of that because we minimize the number of cache misses. However, it might be dangerous in other cases, because if X and Y falls on the same cache line and we have at least one writer and there is a high frequency of reading and writing from multiple threads for X and Y, we end up with a fault sharing problem. And I discussed, not yesterday, but a day before, during my architecture for performance topic, more details about fault sharing problems. So basically we need to pay careful. Reordering fields, it might be dangerous, especially for this situation. And also, suppose they are reordered, they fall on different CPU cache lines, but there are only reads. So one thread reads X and the other reads Y, but because they are on the same thread, but because they are on different cache lines, reading Y probably leads to additional misses. So that's why we need to be careful and conscious about this case. Next one, it's null checks. What happens? Let's suppose we have a method and that method receives an integer, and inside the method we test if it is not null, we multiply by that with 42, otherwise we return. So a very simple method. And we create a benchmark around this, and we call the hot method only with not null values, as in this case. what happens, how C2 optimizes this, because C2 realized there is no nulls that were triggered for the method. Why not to eliminate, to completely remove the null check, right? And here you can see there is no null check in this code. It's just a retrieval from the get field and the multiplication. However, as you can see here, return implicit session dispatches to that address. There is an implicit null check handler. What happens? Because it saw that there were not nulls. However, if there might be a null, it hits this uncommon trap and it switches the execution and probably de-optimizes the code, because the code was optimized for an optimistic consumption. There were not nulls at the runtime. But after the code, it's optimized in this way, and there is a null which happens, a segmentation fault happens, the segmentation fault switches and hits the uncommon trap actually, and it goes into de-optimization, probably switches back to the interpreter and re-optimizes again later on. Clang doesn't do this optimization. Clang sees that it's an explicit null check, so it adds the explicit null check, as we saw here. So if it is 0, it jumps, returns 0. If it is not 0, multiplies by 42, and returns the result. In terms of performance, more or less the same, 1.8 versus 2. Even if there is an explicit null check, I would say on modern hardware, if that branch check doesn't end up with a stall, CPU stall, it's not quite a big difference. So explicit null check in this particular case doesn't make a big difference. These are the conclusions that we already discussed about. And now let's see what happens if we call the hot method in Java with null and not null values. Because initially we called only with not null. And in this case, as you might see, a just-in-time compiler sees there are, null and not nulls, and it optimizes the code similar as LLVM clang did initially. So it explicitly adds the null check and tests. If the instance is null, returns 0, otherwise multiplies the value by 42 and returns. So no any assumption, no any uncommon trap, and JIT falls back to the classical way of optimizing. In terms of performance, it's more or less the same, 2.2 versus 2, a bit slightly slower on the C2 because of that null check. However, I would say fast enough, it's fast enough. It's not a big discrepancy. And you might ask, what would be the cases? Where just-in-time compiler is able to benefit of this assumption, of this optimistic consumption? So this is the case because I included only a test condition, only a null check. However, you have a huge number of null checks conditions, and all of them follow a predictable branch. For example, all of them are not null. In this case, just-in-time compiler it's able to remove all those explicit null checks, but on the LLVM clang, they reach the hardware limit because this has a limit at the hardware level. So the hardware predictor starts falling off the cliff. So in this case, there is a discrepancy in terms of performance between clang and JIT C2. But until that point, if you have just a few such predictable branches, probably on modern hardware there is not a huge discrepancy. Local elision. Local elision says, for example, you have a method, and in that method you have an object, and within that object you have a lot of synchronized blocks using a local instance. Of course, this is a superfluous code. However, you may end up with this situation after inlining. So, for example, if those synchronized blocks were inlined from other methods, you may end up with this code. But otherwise, no programmer would write the code in such way. Even though, if the case, just-in-time compiler, as you can see, there are a lot of synchronized blocks, so there is no contention. Even if two threads you call the same instance, the execution happens on different frames, stack frames. The just-in-time compiler is able to see that and optimizes by completely removing the synchronization. So as you can see, there are 10 additions in sequence, so no locks in between. In comparison, LLVM clang, it's not able to do this optimization. He uses 9 useless locks, and at the end, the last one, it does the sums and return. In terms of performance, JIT-C2, it's definitely better because it was able to spot there is useless synchronization versus clang, which doesn't remove anything, and it's dependent on the number of those useless synchronized blocks. The conclusions, in LLVM clang, it's not able, and the time is dependent on the number of blocks, synchronized blocks. On the Java side, Java benefits of the built-in synchronized semantics, which are very well defined at the language level, and the just-in-time compiler C2, it's able to spot that the object is not escaping, so it completely removes the synchronized blocks. Virtual calls. What happens in case of virtual calls? We have 3 cases. The case of single target invocation. What means single target invocation? It's basically you have a base class, which is shape, and you have a triangle which implements the shape and overrides the method compute. In the benchmark method, the last one at the bottom of the slide, we have that instance, and we call the compute by injecting the instance and the parameter. And the parameter, we assign it to the value 3. So this is the test case. In JIT-C2, the shape of it, what we have, surprisingly, we don't have any virtual call method. It's just a pure 3 assembly instructions that does that the multiplication. So there is no any virtual call, even if in the initial call there was a declaration of the base with the target of the child, and we perform a virtual call actually. And here, just-in-time compiler sees that it's only one target. It decides to inline that target without any uncommon trap. LLVM clang, as opposite, takes the triangle, takes the parameter, and uses the vtable. It uses the virtual call. It still relies on the virtual call in order to trigger the computation. And as we can conclude, there is no any optimization particular in this case. As opposite to JIT-C2, he sees that it's only one target implementation, and it decides to inline and optimize. In case of performance, more or less the same, at least in my test case. JIT-C2 slightly better versus clang, 1.9 versus 2 nanoseconds. However, I would say it's quite a marginal difference in performance. Now let's complicate a bit the scenario. Let's have two targets invocations, basically triangle and rectangle, that extends the shape, and both of them overrides the compute. The test case, the benchmark, it's the same. We have 2 instances, and we call the compute method by first instance and the parameter, plus second instance and the same parameter. So in the end, it should return this 3 multiplied by 17, because 3 is the parameter, plus the second one, 3 multiplied by 19. So very simple math. In this case, just-in-time compiler sees that, oh, there is another possible target implementation, a par triangle, and what it does the explicit check. So it checks actually if the instance is rectangle. If the instance is rectangle, it does a computation. If the instance is triangle, it does other computation. But as you can see in the line jump not equal and that address in red, if we have other possible third implementation, which is neither rectangle nor triangle, it hits the uncommon trap, because he is not sure that there might not be any other possible implementation. So hitting the uncommon trap, It's basically bails back to the interpreter, it de-optimizes and re-optimizes back later on. But still in this case, it relies on inlining because as you can see, it inlines both target implementation and it adds the uncommon trap for another possible third one. LLVM clang, what does? It does the virtual call in both cases. So it triggers triangle compute to compute the first part and then rectangle compute and sums the results and returns the results. So in this case, it still uses virtual function call overhead. In terms of benchmark comparisons, we have 3.9 versus 4 nanoseconds, so not very big difference, I would say. Even if C2 inlines and does the null branch check, still not a big difference, at least on my test. That's why I would say that be focused on the optimizations and put the timings a bit far. And then the last case, we have, let's even complicate more that case, and let's create a third possible implementation, which is square. And inside the benchmark, we trigger compute injecting the triangle instance, plus another compute injecting the rectangle, plus another compute injecting the square, the last benchmark method. And in this case, what we can see, surprisingly or not, JIT it's not able to perform any optimization. And this is basically a lesson that you should take away. Starting with the third possible implementation, particularly JIT C2 in the hotspot doesn't do any kind of optimization. It just do the virtual call. So no any uncommon trap, not anymore inlining. LLVM clang basically does the same. It triggers using the vtable. It triggers triangle compute. It triggers rectangle compute. It adds with the previous, and then square compute and keeps them summing up. And at the end, it returns the sum for all of those three. So in this case, still vtable lookups to virtual calls in case of LLVM clang. In terms of performance, JIT C2 8.1 clang 7 nanoseconds, still more or less the same. However, be focused on the optimization and not quite debate on the figures. In terms of conclusions, LLVM clang used vtable lookups for all of this. However, I tried to cheat a bit the C++ code in order to do that, because you might find situations where LLVM clang does as JIT did for single and two target invocation. It's able to inline, but in this particular context, I tried to cheat a bit the clang compiler to do the vtable lookup. On the other side, C2 was able to inline and optimize for 1 and 2 targets, but starting with the third, it couldn't. Why? Because this context, it's called polluted profile context. So when you change from one implementation to the other, you basically pollute the context. And this, it's explained on that page. You have the URL on the bottom on the wiki.openjdk page. And this profile pollution context has few resolutions. So one of them to be solved is to enable context-dependent split profiles. So enabling context-dependent split profiles, you can actually solve the issue with starting with the third possible implementation without paying the virtual cost. However, this is not implemented. Probably it's targeted at this stage for the 13th release. Hopefully it will come with the 13 JDK release, but until that time, keep this in mind. Starting with the third possible implementation, you pay the cost of the virtual code. There is no any optimizations happen during the runtime. And the last one, it's about Scalar replacement. Scalar replacement, it's quite a nice one. Let's suppose you have a class declared at the bottom of the slide, the wrapper class, which has two fields, x and y. And in the hot method in the middle, you create an instance of that wrapper by 2 parameters. So basically, X it's assigned to parameter 1 and Y it's assigned to parameter 2. And in that hot method, you return the sum of X plus Y. So actually you create an instance for nothing because you create an instance and return an integer at the end. Why should we allocate on the heap that instance? Of course, it's not the case. It's not going into the heap allocation. JIT-C2 spots that the escape it's local. The object scope of that instance doesn't escape, so it prevents the heap allocation and it allocates on the stack. As you can see, it's just a sum between X plus Y without any allocation on the stack, even if the programmer wrote explicitly new. In Clang, Clang does the same principle, the same optimization, because the object doesn't escape. It's even smart ahead and spots that in order to optimize and prevents the heap allocations. In terms of benchmark comparison, maybe the same, fast enough, it's fast enough. In terms of conclusion, LLVM Clang, as we saw, even if does everything ahead, it's able to spot that, preventing the useless allocation in comparison with JIT-C2, which takes this assumption and realizes that during the runtime it needs profile information. Final conclusions out of this talk, LLVM Clang, as you can see, it's very smart compiler. He is able to do a lot of powerful optimization even ahead without any profile information from the runtime, as it was the case for the Scalar replacement and that wonderful optimization of sum from 1 to n. JIT-C2 can do things really in a good way when the runtime information matters and when the built-in synchronized semantics and the language level are very well defined, as it was the case with the synchronization like lock elision and also virtual calls. However, when there are basically the same heuristics of optimizing the code, like we saw in the case of loop unrolling, the vectorization operation, the timings are more or less the same. And in closing, I would say, because I started with a Richard Feynman code, I would say it doesn't make a difference how beautiful your guess is. If it is still a guess, however smart you are, who made the guess? If it disagrees with the experiment, it's wrong. That's why during the entire talk, I decided to prove what really happens under the hood and not just making assumptions. That's why during the entire talk I gave you the evidence. Special thanks to my C++ developer colleague, which spent a lot of time with me and analyzing the assembly, because as I was saying in the beginning, it's not quite a handy work or very easy work. And thank you all for attending this presentation. I'm a bit running out of time, but I'm still here. You can catch me and ask me, and also I will tweet the slides after the talk. So thank you very much for attending.